Good afternoon. My name is Steve Ferguson, and welcome to the Washington Labs Academy webinar series. We hope you'll find the next hour or so very useful and informative. We developed the webinar series to attack problems that our customers face on a day-to-day basis. The engineering compliance issues can be very complex, and we're always looking for ways to help this technology industry. So we certainly hope that this Broadband Devices webinar by Mr. Michael Young will be very informative to you. Before we begin, however, hopefully everyone can see the slide that's on the screen, commercial wireless compliance, and we're dealing with broadband design with Young Consulting Service, Michael Young. A few housekeeping details I'd like to take care of. The attendees' sound is muted to keep the meeting quality as high as possible. Also, a recording is underway that will be distributed to registered attendees at the conclusion of the meeting. It'll take a few hours to process and make it available. We'll be expecting that, along with a copy of the presentation. You may want to select a full screen view for better resolution to see that. To do that, you would hit View Full Screen, so the attendees can clearly make this a full screen on their computer. We'd like to hear from you with questions or comments. You can use the chat or the question and answer function. However, I will not interrupt the speaker to present these questions during the presentation. Please address the questions, either chat or QA, to the host, and I will ask these questions at the conclusion of this session. We do look to hear from you. You can contact us via Washington Labs at academy@wll.com. 301-216-1500, or Michael Young directly, michael.young@cfl.rr.com, or his cell number 703-966-7701. So please let us hear from you if you have anything. I would now like to introduce your presenter. Michael Young was the founder and president, chief technical officer of YDI Wireless, a publicly traded company that designed and manufactured broadband wireless data communications equipment and systems. He designed and his company manufactured a complete range of wireless data communications products and accessories. His company was a world leader in providing extended range, license-free wireless data equipment that included Wi-Fi as well as turnkey long-distance wireless systems for applications such as wireless internet, wireless video, wireless LANs, WANs, and MANs. He left the company in 2004 and started his own small engineering company, Young Consulting Services. He also went back to teaching college as an adjunct professor at George Mason University, where he created their new wireless communications and networking course, as well as being a faculty supervisor for the ECE Senior Engineering Design Capstone Program. Recently moved to Florida, he is set to bring that wireless course to the University of Central Florida in Orlando. Mike, I welcome you to the meeting. I'm going to hand the controls to you. Remember, you're going to share screen because of your animations.
Hi, Steve. Greetings, everybody, and welcome to my presentation today on broadband wireless devices. I presume, Steve, now my screen has come up so you can see it?
It is. You're visible, so please do that. Thank you very much. I'm going to be quiet and listen.
Okay, today the presentation is going to be about broadband wireless devices with a focus on what's available today, what frequency bands are available, and that's what we're going to talk about. I just saw this new access point by D-Link that's a dual band access point with all the antennas sticking up. I thought it was very interesting looking, so I threw it on the screen here. Well, what is the definition of broadband wireless? Well, according to 802.1.16-2004, the WiMAX standard, broadband means having instantaneous bandwidth greater than 1 megahertz and supporting data rates greater than 1.5 megabits per second. Well, the FCC recently redefined that definition to mean download speeds of at least 25 megabits per second and upload speeds of at least 3 megabits per second. But there are a lot of broadband wireless systems out there that are point-to-point, and so up and download definitions really aren't relevant, and people have defined broadband wireless in several ways other than these two listed here. For example, in the licensed wireless systems, we have licensed cell phone systems and personal communication service systems on the 1.9 gigahertz band. We also have licensed point-to-point microwave links on 6, 11, 18, 23 gigahertz, etc. These are licensed systems where you have to own a license to the radio frequencies to operate. There's also some important license-free bands. The Wi-Fi band at 2.4 and 5 gigahertz, the ISM band at 900, 2.4, and 5 gigahertz, mmWave bands at 24, 60, 72, and 80 gigahertz. White spaces on UHF TV channels. Very interesting. We'll talk about that too. And the new Citizens Broadband radio service in the 3.5 gigahertz band. So this discussion today will only be on the license-free bands. I'm not going to cover the cell systems or the point-to-point microwave because only the licensees can use them. But we're going to talk about bands that anybody can deploy on these frequencies. So first we're going to talk about Wi-Fi. I'm going to give an overview of Wi-Fi and then go down to each band and talk about the bands, its characteristics, its features, and some products that are available today. But let's start with Wi-Fi. As you probably know, Wi-Fi means wireless fidelity. And it was a term set up by the Wi-Fi Alliance back in 1999. And they certify 802.11 wireless LAN devices to make sure they're all interoperable. That was the goal of the Wi-Fi Alliance. The license-free Bay radio bands we're going to be discussing today, 902 to 928 megahertz, the 2.4 gigahertz band, the UNII band, the 5725 to 5850 megahertz band, that's an ISM band, the 24 gigahertz band, 60, and the 72, 89, and 90 gigahertz band. The 802.11 A, B, G, and N live in these two bands. Here's a summary of the protocol because everyone gets confused with all the letters, and so I organized it in the order in which these things were ratified. Very first was 802.11, 802.11, which is frequency hopping spread spectrum and direct sequence spread spectrum. It's 2 megabits per second on the 2.4 gigahertz band. This is back, you know, in the 1999-2000 time frame where some people had frequency hopping on 2.4 and some people had direct sequence spread spectrum. And so when I had the meeting of all these vendors and other parties, they came together and said, well, we'll just make it 802.11 and we'll support both frequency hopping and direct sequence spread spectrum. At that time, it was so naive, there was no letter after. It was just 802.11. Man, 2 megabits per second over the air, that's fantastic. Because back then, what did you have? You had T1 lines, 1.544 megabits per second. You had, you didn't have DSL yet. You had the 64 kilobit per second phone links. So 2 megabits per second seemed good. But then they came out with a new way of encoding the data, and they came out with 802.11b, which is direct sequence spread spectrum, 11 megabits per second air data rate on 2.4 gigahertz. Simultaneous with that, they were working on this new technology, orthogonal frequency division multiplexing. Of course, this was only possible with the advent of small, low-cost digital signal processing chips that could take a baseband, a radio signal modulated, carrier modulated, put it to a low RIF frequency, and then do a analog to digital conversion and do software to demodulate it and also modulate the signal. Because if you were to do OFDM and discrete circuitry, you would just need so much chips, it's just not practical. So it's all thanks to digital signal processing that we have the cell phones today and 802.11a and b. 802.11g came afterwards because, once again, we had all those 802.11b products on direct sequence spread spectrum, and they didn't want to leave them in the dust, so they had to come up with a compatibility solution that would support OFDM for those units that could talk that, and direct sequence spread spectrum. So 802.11g runs 54 megabits and 11 megabits on direct sequence spread spectrum on 2.4 gigahertz. In fact, there's still a lot of 802.11g devices out there in use today. Then 802.11n came along and said, well, you know what? We want to be able to offer more features. We want to have MIMO, multiple in, multiple out antennas. So we take advantage of multipath signaling as another channel to send data. We want to take advantage of combining channels together so that instead of a 20 megahertz wide channel, we can have a 40 megahertz wide channel and double the data rate. So 802.11n was an enhancement and merging G and A together, if you will. But they're not done that now. They even came out with 802.11ac, which is OFDM. And now they can combine even more channels. I'll show you the frequency spectrum there in a minute to get 1.5 gigabits per second over-the-air data rate, which is kind of difficult to do if you just have a GIGI interface on your access point and your router. I don't know how you're going to get 1.5 gigabits through that. But in any event, the over-the-air data rate with strong signals and combining the maximum number of channels together, you would get an air data rate of 1.5 gigabits per second. And now recently, they've come out with 802.11. By the way, that's a typo. It should be 802.11 AC, 802.11 AD. I just noticed that. They've come out with 60 gigahertz devices that could run OFDM or BPSK, QPSK, or 16 QAM. And you can get up to 6.7 gigabits per second with OFDM or 2.5 gigabits per second with 16 QAM. Here's the overview for the 802.11 from a different standpoint. We have the original 802.11 that came out in 1997, 2 megabits direct sequence spread spectrum. 802.11b came out with its CCK encoding using direct sequence spread spectrum. Then 802.11a came out, and a subset of that is 802.11g, which is the exact same modulation as 802.11a, but it's on a 2.4 gigahertz channel. Then .11n came out with a sub .11ac and .11ad on 60 gigahertz. And then they have 802.11p, which I'm not covering because I don't think this has really been implemented yet. That's where you have wireless vehicle access where they can talk to each other, car can talk to car, and they're actually on 5.8 gigahertz. They're actually outside the Wi-Fi band. And then 802.11af, which is the TV white spaces. The interesting thing is I hear so many vendors and non-technical people say, oh, this is a Wi-Fi fill in the blank. Well, if it ain't an 802.11 whatever, it's not Wi-Fi. But because the general public understands the concept of Wi-Fi as broadband wireless data, they use the term Wi-Fi. As an engineer, I just don't like that term. So, and by the way, the little x, there is an 802.11 capital X, which is a protocol used for authentication. The little x I have in my little screen right here basically just means 802.11 fill in your alphabet soup. And there are a lot of other 802.11 specifications out there too that are beyond the scope of this discussion, so I'm not going to mention them. 802.11g, as we know, has 3 non-overlapping channels on 2.4 gigahertz, and this really leads to an interference problem. There are 802.11g access points everywhere. I mean, everywhere. You just go just about any place and you'll see several. And here is the problem. There are so many out there operating on 2.4 gigahertz that they're interfering with each other. I'm living in Florida now, and we have Bright House Networks, and they put in a hotspot access point at every business location they deliver internet access to. In my office here in Winter Park, Florida, I have one of those Wi-Fi hotspots from Bright House, and right next to it I have my access point that I use for my local office on different channels. And you just go down the street and there are so many of these access points, and they're jamming each other. So that was a significant and still is a significant problem with 2.4 gigahertz 802.11g and .11n products that work on 2.4 gigahertz. So channels 1, 6, and 11 offer no adjacent channel interference, and everybody's trying to put all these access points on these 3 channels. Now, in 802.11a, they have various data rates depending on whether they modulate with BPSK, QPSK, 16 QAM, or 64 QAM. So the difference between, for example, 48 megabits per second and 54 megabits per second is simply the coding rate, where the coding rate is defined as the number of bits sent divided by the total bits sent. So when you're at 48 megabits per second, you have 64 QAM, and at 54 megabits per second, you have 64 QAM, and the difference is how many redundant data bits you send in order to get an error-free packet. So this is just an overview to show the various data rates, and all of the modulation data rates a unit connects at is a function of the SNR. If it tries to connect at 54 and it can't, it'll try 48. If it can't do that, it'll step all the way back to BPSK, which is the lowest order of modulation and the minimum amount of SNR needed to connect. So 802.11g is identical, but it's on the 2.4 gigahertz band. This is the spectral density mask defined by an 802.11a or G access point. Basically, as you know, with the FCC, they want to know where the 20 dB down point is from the center frequency, and this is occupying plus or minus 11 megahertz, or it gives a 22 dB occupied spectrum for 802.11g and A. The interesting thing is people have bought and installed amplifiers, and that's one of the things YDI Wireless did, is we made amplifiers. And many of these amplifiers are not linear amplifiers, and what happens is they compress and spread out the occupied bandwidth by raising that first shoulder up, and it no longer complies with 802.11g or A, and also will interfere with the adjacent channels. So when you design a system with an amplifier, the whole system has to be FCC Part 15 certified with the radio, the amplifier, and the antenna, and you must comply with this spectrum mask. 802.11a is very clever because they have 12 non-overlapping channels. This, I think, is the key to success of Wi-Fi, is these 12 non-overlapping channels. Many access points now are coming out today with dual channels, 2.4 and 5 gigahertz. And many devices like iPhone 5s and up and tablets are now supporting .11a as well as .11g. And when you go to .11a on 5 gigahertz, of course, your range isn't as good because free space loss and penetration through walls is not as good as it is at 2.4. But if the channels are assigned properly in any given area, you can get virtual interference-free connectivity on one of these 802.11a 5 gigahertz channels and see the true potential. But 2.4 is still the predominant frequency band used. Now, 802.11ac, which is the next step past 802.11n, what they bring to the table is, hey, let's combine lots of frequencies together. So if you take a look here, we have the standard 20 megahertz channels used in 802.11a. And by the way, sometimes when you configure these things, they'll show channel 108, 112, 116, et cetera, et cetera. And so if you're ever wondering what those channels are, here's a quick table you can look at. Notice it goes from 36 to 40 because they have channels in between that are not Wi-Fi authorized channels, but they're frequencies that some equipment lets you go on those channels. So what they've done then at 802.11n is allow you to combine 40 megahertz channels so you can get double the throughput, as you can see on this line here. But 802.11ac, it says, why stop at 40? Let's go to 80. And now they combine the channels like this. And why stop there? let's go to 160 megahertz wide channels. And they have 2 of them. And they said, why stop there? Let's have some down at the 5.1 band and some down at the 5.5 band as well. And then also down here, this one too. So this is what 802.11ac brings to the table. Basically, it's OFDM on channels which are combined in various capacities. And the mask for that is shown here. It's similar to what is on the 20 megahertz channel. Basically, your 20 dB points are going to be 21 megahertz opposite the center band of the carrier, or 41 megahertz where the 20 dB points are down. On the horizon, I still haven't seen many products like this yet, is 802.11ad, which operates in the 60 gigahertz band. 2 gigahertz of RF spectrum are available. Just think about that. 2 gigahertz of RF spectrum. That's mind-numbing amount of bandwidth. You can get extremely high data rates, up to 7 gigabits per second. However, very short range, maybe several yards indoors. They have an alliance for this called the Wireless Gigabit Allowance, known as WiGig. And they're the ones that are going to set the standard so that if you buy a device from company A, it'll work with your device from company B, just like Wi-Fi. But the WiGig tri-band-enabled devices will operate on 2.4, 5, and the 60 gigahertz bands. So the question then comes, on the license-free bands, who really cares about those non-Wi-Fi uses of the license-free bands? Lots of folks. Consider the key features to all these license-free outdoor broadband links. First, they can be deployed immediately. You can just put them up and you're on the air. No engineering survey or FCC application is involved. You don't need to dig trenches for cables. There's no recurring costs of lease lines. You don't have to contact the local phone company and pay some god-awful amount to get a fiber connection from here to maybe a mile away. And what winds up happening is it pays for themselves in months, maybe longer, depending on the band and the data rates, because some equipment obviously is more expensive than others. And it will be there for as long as you need it. So, what's the downside of using these license-free bands? Well, there is a risk. The price you pay for using this license-free frequencies is you must tolerate interference from any other system, license-free or otherwise. You have no recourse as far as legal or FCC remedies. If you're getting interference on a license-free band on your device, you have to deal with it. It is a condition that is part of your FCC Part 15 grant. In fact, on the back of Part 15 devices, it'll say a statement that you must tolerate interference on this device. And this is why most telcos and cell companies avoid the license-free bands. They will pay the extra expense to get a licensed microwave link to protect them from interference to ensure reliability. In fact, we were approaching Verizon and other companies saying, hey, we got this great license-free product. None of them would use it because they need to know that they're protected. They have virtually zero chance of getting interfered with. And if they do, they have legal recourse to shut the interference down. However, there are technical solutions that could virtually eliminate this risk and assure reliable links. And stay tuned, we're going to talk about some of them. So let's talk about the first band, the UNII band, which stands for Unlicensed National Information Infrastructure. Only the FCC could come up with a name like that. But Wi-Fi lives here, but its protocols do not support long-distance operation, even if you have strong signals and good SNR. So if you took a 802.11n or G access point and just put an amp on it or not, hooked it up to an external high-gain antenna, you would find that it would not work because of the propagation delay. So besides 802.11an and AC, there are a lot of Wi-Fi equipment available for use outdoors, both point-to-point and point-to-multipoint. We ran smack into that when we started developing our outdoor solutions. We found that once you got past about maybe 2 miles, a mile or two, the ACNAC protocol broke down. Because what happens is, in an 802.11 protocol, it sends a packet out and it waits a certain amount of time to get a reply. If it doesn't get a reply, it presumes it was interfered with and it'll send it again. In the meantime, while it's transmitting, the other unit is replying back. With a propagation delay of 5 microseconds per mile, if somebody's 2 miles away, it takes 10 microseconds to get there. It's got to be processed by the receiving end. Receiving end has to go into transmit, put a packet together, and send it out, and that's another 10 microseconds to get back to the base. And that 20 microseconds is too long for this wait time, this delay time built into the wireless protocol, and it says, oh, I'm going to send it again. And what happens is it just goes down to the lowest air data rate no matter how strong the SNR is. So while people may use the original 802.11g or .11a wireless card, they throw the protocol out the window, use that wireless card, and have their own protocol, like TurboCell from CarlNet or Proxim's version of that as well. So the low UNII band has got frequency from 5.15 to 5.25 gigahertz. Originally it was indoor use only, low power, but now they authorized 36 dBm EIRP, point-to-multipoint, or 200 watts, that's plus 53 dBm, point-to-point is now allowed. The mid-band, 5.25 to 5.35, and the worldwide band, 5.47 to 5.725, can be indoor and outdoor, but this band is subject to dynamic frequency selection, DFS, or radar avoidance. I heard somewhere that the Patriot missile system operates in this band, and I don't know if that was rumor or scuttlebutt, but if you see a signal that looks like radar, you have to change frequencies. And the device has to be tested in the lab to verify that that works. They subject it to the same pulses that this radar would have, and they define the pulses and all, and the frequency, and your unit's got to hop off that frequency. And then the upper band, which overlaps with the ISM band, is 1 watt transmit power output and virtually unlimited EIRP with high gain directional antennas. You can go 50 miles on this band with 1 watt transmit power and high gain directional antennas. Now, manufacturers got to get their equipment certified under the higher power ISM rules for 5 gigahertz, obviously. But they provide a very long-range point-to-point link with high-gain antennas. And these are some typical products that are on the market today to give you an idea. They integrate the antenna right with the radio. Of note is a product from a company called Ubiquity Networks, their Air Fiber. This particular device operates on 5 gigahertz, has a very unique approach. It operates full duplex on the band, has 2 separate antennas, and antenna 1 is transmitting on frequency A, and antenna on the other side, the other antenna is transmitting on frequency B, and you get full duplex operation, which gives you incredible data rates and really great range. There are many non-Wi-Fi devices in this band, and many are used by wireless internet service providers to provide backhaul to the high sites. That's one of the things that we did. We offered this solution here, where we have point-to-point links from the internet access point to high sites, where they will have point-to-multipoint connections to residential or remote subscribers. So in rural, less populated areas, wireless internet service providers called WISPs offer broadband internet access on these license-free bands. Those were our main clients back with YDI Wireless, and they're still doing it today. From these high sites, they use 2.4, 5.8, or 3.5 gigahertz bands for point-to-multipoint wireless connections to their fixed clients. Many rural areas where there's no fiber or no cable deployed because there's no payoff to do it. They have their own organization called Whisper with over 800 members. And basically, they set up a high site, and they talk point to multi-point to their clients. And they would have a dish antenna or a flat panel antenna, typically integrated with a radio at the client site in order to get their broadband internet access. Millimeter wave devices. Let's start with the 2.4 gigahertz band. It's just above the 23 gigahertz license band. It has the frequency of 2400 to 250 gigahertz or 250 megahertz of bandwidth. Point-to-point systems only authorized, and several vendors offer links in this band with integrated antennas. They look something like this, where you just bolt it on the pole and you aim it. Typically, they run power over Ethernet. Some have external power that comes in. And there are various operations. Most of these that you see on the screen now operate time division duplex. But the state-of-the-art is this Ubiquiti AF12 fiber, air fiber. It's basically the same concept down as the 5 gigahertz version. That's over on the right. You see what it looks like without their radome on. There's plastic, and they have a metal reflector there with 2 radiating elements. This guy features dual independent 2x2 MIMO antennas with 24 gigahertz high gain integrated dishes. And it can operate full duplex using frequency division duplexing or hybrid division duplexing. But an interesting thing about this, what gives this particular approach is something that the FCC limits your EIRP. So you can only have so much transmit power when you combine the antenna gain and the transmit power feeding that antenna. But you want a higher gain receive antenna. So what they've done, which is very clever, is they have the bottom antenna is transmitting, so it doesn't exceed the EIRP, but the top antenna is receiving, so we can have maximum gain. And this is a very interesting approach, and as a result, it has unparalleled speed and spectral efficiency in the 24 gigahertz band worldwide. Now the question is, though, why did the FCC give the 24 gigahertz band away free? Most people may not realize this, but the answer is 24 gigahertz is the resonant frequency of the water molecule, and hence it limits its range. So let's take a look at this chart right here that shows absorption in the atmosphere due to vapor, water vapor, and oxygen. The atmosphere resonates at 24 gigahertz, where the oxygen molecule is resonating. A lot of people think that microwave ovens are 2.4 gigahertz because that's the resonant frequency of the oxygen molecule. It is not the resonant frequency of the oxygen module. The oxygen molecule actually resonates at 24 gigahertz, but it does vibrate at the subharmonic 2.4 gigahertz band, and that's why microwave ovens operate in that band, and that's why the 2.4 gigahertz band is a license-free band, because there are all these microwaves coming out in the late 50s, and they said, well, we can't give this band to anybody, so let's just make it a free-for-all. Likewise, with the 24 gigahertz band, you're going to have an additional 2 dB of attenuation per kilometer simply because you've got water vapor in the air. Now notice, too, the oxygen molecule resonates, while we're doing this, at 60 gigahertz. So that they gave the 60 gigahertz band away because people wouldn't want to use it. How could you sell that band? Because you're going to get an additional 10 dB, actually 12 dB per kilometer, simply by having water vapor in the air. This is in addition to free space loss. So the range of 60 gigahertz is pretty limited. So they call this band the V band. Actually, the spectrum is 57 to 64 gigahertz. It's 7 gigahertz of unchannelized spectrum, meaning you can put anything you want in there. and they gave this band away free due to the massive O2 absorption in the atmosphere. No one would be willing to pay for it. Indoor uses would be, well, 802.11d uses this band. Good application for this, and I predict this is coming, wireless video and audio from your computer or set-top box to the TV. I see it probably as a replacement for your HDMI cable. You can have your set-top box there, connected to your cable coming in, and no wires going up to the TV. This means the set-top box has to be 802.11ad compliant, and the TV has to be 802.11ad compliant. My gut feeling is they're going to go in this direction, and that's what we're going to be seeing in the years to come. Another interesting thing about the 60 gigahertz band is you can go outdoors, but again, the O2 absorption assures short range. In addition to that, rain fade is the limiting factor, because now you're starting to get on the order of magnitude of the raindrop, and you'll get scattering. More on rain fade later. In 2013, the FCC allowed more transmit power. They increased it from plus 42 dBm to plus 82 dBm for devices using an antenna with gain greater than 51 dBi. You can get a 51 dBi antenna a little over 2 feet in diameter, so it's not a very big antenna. Having said that, the beam width is really narrow. In fact, they use very narrow beam dishes. That'll assure virtually no interference. It's almost like a laser beam, and aiming is very critical. The beam is very narrow. But because it's very narrow, you're able to ensure that you're only looking at your antenna on the far end, and unless somebody was literally right behind it, you wouldn't see them. Further, in order to intercept the 60 gigahertz band, you have to put something up right in the middle of that beam in between the two antennas, which is kind of difficult to do. So to me, the 60 gigahertz band is a great band because you're probably not going to get interference from anybody. By the way, in space, military uses this band for satellite links because it cannot be received on the ground through the atmosphere. And that's a good way for satellites to talk and not worry about anybody picking it up on the ground, because it ain't going to make it to the ground. Now, before the FCC increased the EIRP by 42 dB, this was the maximum range recommended for a 60 gigahertz link. My company sold a 60 gigahertz link, and this is what we recommended to folks. Notice down in the south where I am, here in the Orlando area, 600 meters is the maximum length they recommend. 700 meters here. Now, if you're in Denver, you'll probably do 1,100 meters and 1,000 meters in this part of the country. But I think industry pressure made the commission realize that more transmit power was needed to overcome this O2 and rain fade. And that's what they did. And the compromise the FCC came back with, okay, we'll do that, but you got to narrow the beam width of your antenna so that you don't throw that signal so far around that you'll cause interference with somebody else. The 72, 80, and 90 gigahertz band. That's called the E band. It's 71 to 76 gigahertz, 81 to 86 gigahertz, and 92 to 95 gigahertz. It takes special chips to make radios operate on this frequency. Only point-to-point links are authorized. You get extremely high data rates, greater than gigabits per second. And you get no O2 absorption. That's a big plus. However, rain fade and free space loss is much more a factor. Typically used for cell tower backhaul or connecting buildings or cell towers over a distance of a few miles, if properly engineered. For example, can your 72 gigahertz link take a 36 dB hit when the rainfall is 3 inches per hour like it is sometimes here in Florida? And here's what I'm talking about. Let's look at the rain fade chart. On the left, we have attenuation in dB per kilometer. We have negligible attenuation down here, 1 dB up here. So if you're less than, say, 6 gigahertz, even with the highest rainfall of 150 millimeters per hour, that's the right, if this is precipitation in millimeters per hour, 150 millimeters per hour is 15 inches per hour. That's like a waterfall. Even if you had that, it would only be at 6 gigahertz about maybe a dB and a half loss per kilometer. However, above 10 gigahertz, one needs to start taking into account rain fade. Because at about 10 gigahertz, we're now talking about, we're getting it up into this part of the chart here. Note the log scale and that the precipitation over here is in millimeters per hour. And a 1 millimeter is simply just a trace precipitation. At 66 gigahertz, 100 millimeters, that's 10 centimeters per hour, only adds 0.6 dB per kilometer. So if we went 6 gigahertz, you went up here, and you had 100 millimeters, which is this one right here, you only have about 0.6 dB. It's negligible. However, at 72 gigahertz there, if you are 25 millimeters per hour, which is about an inch of rain per hour, which is, a thunderstorm will do that easy. So you've got 25 millimeters per hour here where the arrow is. You can expect 12 dB right there, coming across, 12 dB per kilometer. So if you have a 3-kilometer link and you had that kind of rainfall of an inch an hour, you're going to need an additional free space loss of 36 dB. Sorry, an additional system gain of 36 dB. So that's one of the main disadvantages of 72 gigahertz is trying to go longer distances in heavy precipitation. The link's going to fail. There are a few vendors out there in the 60 and 72 gigahertz who actually have built in a backup radio on 5.8 gigahertz. It's got a lower throughput, but if your 60 or 72 gigahertz link goes down, you have a lower throughput, but you'll still have backup on 5 gigahertz. White spaces on the UHF frequencies. So this was spawned from the FCC's desire to make more UHF and VHF bandwidths available for wireless broadband communication. Let's face it, there are a lot of unused UHF and now VHF TV channels which are just not being used. So they termed this TV white space. That's what they call this unused TV spectrum. It was adopted under FCC Part 15701 to allow unlicensed radio transmitters to operate in these television spectrums at locations where the spectrum is not used by licensed services. The rules allow applications similar to those deployed in the 900 2.4 ISM bands and the 5 gigahertz UNII bands. But how are you going to know, before I do that, the FCC has dictated specific modulation or protocol requirements for the TV bands, allowing white spaces to be employed in a wide range of devices and applications on an unlicensed basis similar to Wi-Fi. However, this is what I found with my research. They are very restrictive on the emission levels near the edge of the band, probably more than is really needed, I think, thanks to the National Association of Broadcasters. Because you have to have so low a signal at the edge of the 6 megahertz band on that channel, you cannot really operate the full 6 megahertz to carry data because of that classic OFDM slope down near the edges. So you have to operate in perhaps 4 megahertz of the band that you can actually use of the 6 in order to get data out. And that really is going to inhibit your throughput. So while propagation at UHF frequencies is great for non-line of sight, this limits the air data rate considerably and it's not so attractive. And that's probably why you've never even heard of it, is because there are not a lot of people out there doing it. In fact, the FCC has insured incumbent TV band spectrum users, that's TV broadcasters, public safety, registered cordless microphones. You know all these cordless microphones you see everywhere on stage and in TV and all, they're using the UHF white spaces. And they're concerned that someone's going to come in with a license-free device and cause interference right in the middle of a show. So what has to happen is a company called Spectrum Bridge has set up a database that ensures that certain incumbent users are protected. And the equipment that runs on the TV white spaces has to connect to this database, where it's located, and find out, hey, what are frequencies we can available to, and let's go to those channels and use them. And the available channels may vary over time depending on the TV broadband device location and type. So not only do you have a narrowed spectrum in which you can operate on, you have to have, your devices have to be able to contact this Spectrum Bridge database and say, hey, what channels can I use in this area? And you have to stay on those channels. So the key limitation is they have very restricted power levels at the edge of these channels, so they really can't broadcast or provide really true broadband connectivity. Carlson Wireless products, they're the ones that were FCC certified to use with Spectrum Big White Spaces, and that just occurred last year. So if this interests you, you might want to contact Carlson Wireless. I have no interest in any of these companies, by the way. But you might want to contact Carlson Wireless and to get more information about their products and follow up with them. But the better applications are in developing nations, not in the U.S., because we've got so much broadband connectivity now. We've got DSL, we've got cable, we've got LTE. But in developing nations, a lot of them don't have that, and it might be very attractive to have long-range, non-line-of-sight links. This is very interesting. Citizen Broadband Radio Service, CBRS. This is shared wireless broadband use of the 3550, the 37 megahertz spectrum. That's 150 megahertz of spectrum now available in the 3.5 gigahertz band, and it was established on April 17th, 2015, not very long ago. It's found in Part 96 of the Commission rules if you want to look that up. This new band is designed to support activities including small cell deployments, fixed wireless broadband services, something the FCC calls general consumer use. Like CB radio, the licensing requirements are attached to the FCC-approved communications equipment, meaning you don't get a radio license. So there's no requirement for individuals to obtain a license, even for commercial use. 10-4, good buddy. This is very interesting. This is like a very new idea of having basically a citizens broadband radio service that can open up a whole bunch of applications that we're not even thinking of yet. So I commend the FCC for doing this. However, there is some issues with it. It's governed by a 3-tiered spectrum authorization so that you can accommodate variety of commercial uses on a shared basis with incumbent federal and non-federal uses of the band. So there's the incumbent accents. These are the people who are already there, and maybe they're a WiMAX deployed system, and they have what they call a easy license or a soft license to get. They basically register, say, I'm on this frequency band, and here's my equipment. You don't need an engineering survey. Priority access, that's people who have priority over everyone else. And then general authorized access, which is everybody else. Most of the WiMAX equipment deployed operates in this band. WiMAX was supposed to be the big thing. When everyone saw how popular and prolific Wi-Fi was, they saw that it was great, but what was its limitations? Range and power. You couldn't operated far, and the range was very limited. So the concept of WiMAX was, hey, we'll take that same basic OFDM stuff, make it more flexible, varying channel spectrum occupation based on what the licensee can get. Can it get 2 megahertz? Can it get 5 megahertz? What frequency can it get in the 3.5 gigahertz band? WiMAX was also considered a contender for LTE, but everybody decided that LTE was a much better technology, and WiMAX just was now relegated to typically the 3.5 gigahertz band. And it just did not take off, because 3.5 gigahertz doesn't have such great propagation, and you can't use it to provide communication to portable and mobile devices. Doesn't penetrate walls as well, doesn't penetrate buildings. And so it wound up just being stuck on the 3.5 gigahertz band, point to multipoint. And it's good, and it works, but you need line of sight back to the base. So that concludes the presentation with the various pieces of information about the unlicensed spectrum. So at this time, I'm going to open the floor to any questions.
Well, thanks, Mike. I did get a question come in, but I'm not sure it applies. You mentioned the 802.11ad. You think the advent is box-to-box direct communications, etc. Do you know if the direct TV system Genie uses that type technology?
That's a good question, and the answer is I do not know, primarily because I have cable TV and not direct TV, but that's something that I don't know. It could very well, but that means the TV has to support it as well, and I don't think it's widespread in TVs yet.
Well, I'm a direct TV user, and I know that my son has these small modules that just plug into his TV for distribution, and I was thinking maybe that's what this is, but that's why I have a question.
And the answer is I don't know. It probably is the 60 gigahertz band, but is it 802.11ad compliant? I don't know. Okay.
Another item, and it may be off your given subject of unlicensed, can you kind of discuss the shared spectrum use that's being discussed and planned?
I'm not an area, I don't have expertise in that, so I'm really not in a position to give you any comment on that.
Okay. Good question, though. That's the ones that have came in at this point. I'm going to take control of the thing to kind of do a little bit of marketing thing that I need to do. And you should stop sharing so you'll be able to see this event. But okay. I do want to discuss some upcoming training provided by the Washington Labs Academy, where we've done quite a few webinars this calendar year, and we're planning next year's events to have equal or more because we're growing in that area. But this year we completed a Bruce six-pack, or Bruce Archambault's design series, with 6 different webinars. I completed in June, but the recordings are available. A wireless device approval, guess what? One of them was today. You just finished it, so there's one more session planned for this year. I think it's the Far East requirements, Japan and China in particular. Wireless device immunity testing is this week. Tomorrow, Steve Costro will be presenting a discussion on wireless device immunity and its particular requirements. So if you're interested in that, please sign in. Mill Standard 461 testing. Next week, there's a course that does a hands-on thing, 4 days worth in Gaithersburg. There's still a seat available to sign up for that one. Product safety series, we go into next month with risk analysis. This is an 8-part series that's been going on much of this year. And I found a very interesting laser facility safety on October 7th, presented by Peter Bowden, one of the contributors to Z136, which is the North American, OSHA, and Canadian requirements for facility laser safety. And he has a guest commentator planned, a legal person, an attorney, that just worked out an issue where an injury caused a student to have physical harm. And so the litigations are there. So those insurers and facility managers really need to be aware of the OSHA requirements, because in their case, the manager wasn't aware there was a requirement and didn't have things in place. We also look at customized training at your pleasure hours with webinars and multi-part series. I do want to see if there's any other items that have came in. I do not see anything. So I'm going to close this event on behalf of myself, Mike, and the entire Washington Laboratories Academy staff. We wish to thank you for attending and look forward to seeing you on many future events. I'm going to look one more time. No additional questions. Mike, thank you very much for your great presentation. It's a very interesting topic. And,
you're welcome. I'm glad I could do it.
Very good. And I'm going to go ahead and close the event at this point. Thank you again for attending.